At a particular moment, two cars are 45 meters apart, with the one car aiming to pass the other. The car in front is traveling at 12.5 meters per second, and the second car is traveling at 17.5 meters per second. How long does it take for the second car to overtake the leading car, assuming they both maintain their speeds? Now, this question has a lot of numbers and is a very math sounding question, I would say. And we could ask, like on the key concepts page, what concept are we looking at here? And it may not be immediately transparent. But to help me figure this out, I'm going to draw a little picture of the situation because that's going to help me to think about it. And so let's see. We have a lead car that's traveling more slowly, a second car that's traveling more quickly and is catching up, right? So maybe this will actually be the second car then here because this one's not the one to lead. And I'm just going to draw a little whatever thing, okay, and then put some wheels under it. So there's one of my cars, okay. Here is like the other car. Again, your pictures don't need to be, if you're a really good artist, you can make them way better than mine, but there's no need for your pictures to be like good to get the thinking correct. And maybe what I'll put into this picture is I'll clearly state, okay, this represents that 17.5 meters per second because that one's going faster. This one's going along a little bit more slowly. Maybe it's because I'm driving it. I tend to drive kind of slow. Gets slower the older I get, but anyways. Okay, I don't know if I need, well, it looks like the road's going to get bumpy there. Anyway, that's maybe good enough of a sketch for me. I should recognize that initially there's a 45 meters distance between the two cars. Now, let's say that I established, this is like a snapshot of the moment when time is equal to zero, like the moment that's described to us in the question. And I'm going to make kind of an arbitrary choice to say that the origin is here for the second car. And then if I want to describe, again, that second, I'm just going to call it the second car because I've really got just two cars. So I'm going to say first car, second car, okay? Second car is the trailing car. But I'm going to start with that one because that one starts at the origin. And in that sense, I think if I wanted to say what is its distance as a function of time, that would just be the rate formula. So, oh, the connection with the key concepts page is suddenly becoming more obvious, right? Because d is equal to vt. But in this case, I think v for that second car would just be 17.5. Now, in physics, we normally use meters per second, but what I'd like to do is I'm going to kind of borrow from math function notation. So this is not d times t. This is d of t. T is going to be the independent variable, and 17.5 times t is my function. And this is really, since this is the second car, physicists really love to use subscripts. That's something you see maybe a little less often in math classes. But in this class, we're going to start doing that because it's how we tell the story and turn it into math. So it's a skill that we're learning in this class. So that's the second car. That's its function. Distance is a function of time. And I think that's going to let me solve this question. This is definitely a method that is there in physics. Now I'm going to do a similar thing for the first car, and I'm going to try to describe its distance as a function of time. Now we know that its rate is slower. It's in the picture, it's only going 12.5 meters per second. But the thing is, it didn't start at the origin. When time is equal to 0, it was already at 45 meters the way I've set this up. So that means I'm going to start by putting in a 45, and then I'm going to add to that the 12.5. This is maybe a slightly, whoops, make sure that decimal point is kind of, well, hope, does everyone see it? Because it's not that clear. But add to a 12.5 times t. So this is kind of like a modified use of the rate formula. I had to add to vt. I had to add some like initial distance to it because it didn't start at the origin. But these are like two functions. And so again, the mathematical approach to this is just to say, okay, we got these two functions for distances. These two cars are going to pass when those are equal. And so this is like an intersection problem in math. And so the way that this turns out then is you get 17.5t is equal to 45 plus 12.5t. And I want to mention that, I think I was thinking about earlier, but I forgot to mention it explicitly, is I've dropped all the units in doing the math notation, but when I get a final answer, I'm going to have to bring the unit back, and that's okay. Normally in physics class, in many physics texts, many physics teachers will say always write units, but if you're going into math land for a little bit, I'm cool with it as long as you don't have any conversion issues come up, and that's what we're doing here. I think I'm going to subtract from both sides 12.5t, so I'm going to get 17.5t minus 12.5t is equal to 45, and then I can combine like terms here since the difference between the two numbers that are multiplying the variable t is just 5. This is just really 5t is equal to 45. Oops, that 4 didn't work out there. And at that point, you divide by 5 on both sides, and you'd get t is equal to 9, because 45 divided by 5 is 9. But I just said units. It's easy to forget when you're in math land. This is physics land again now. We have to put in the units, say 9 seconds. So, wow, that seemed really complicated for such a maybe straightforward question. What could have been an easier way? What if I'd looked at this maybe from the perspective of the lead car? Okay, so I'm going to say the way a physicist might write this is they would say, let's look at things from the perspective of the first car's frame of reference. And from that point of view, they're seeing a car behind them that is traveling at 5 meters per second faster than they are, which means really in that frame, the speed of that second car would just actually be 5 meters per second. And the distance that car has to traverse is 45 meters. And in that sense, if d is equal to vt and you're trying to solve for t, t is just equal to d over v is equal to 45 meters divided by, whoops, I'm getting on the edge of where I can write very well, divided by 5 meters per second, which in turn, if you look at the way the units work out here, is going to give you the same answer of 9 seconds. Now, the second way that I've looked at this is the physicist's way of doing this problem. This first way is the math way. I'm going to label it. Does that mean physicists never do this way? Well, no, we do this way sometimes too. And sometimes we do it another way. That's maybe you probably wouldn't see this way as much in a math class, but math methods generally are allowed in physics class. But again, we do have these different styles. One's a little bit more conceptual. One has maybe a little more algebra involved. Physicists often are in the habit of reconceptualizing things, sometimes to save a little time on the algebra.